Technically, up to this point in time, we've been doing classification of blood gases. So we've basically been saying what the primary disorder is, whether there's compensation present, what the degree of hypoxemia is present, et cetera, et cetera. Interpretation's a little bit different because we get to use calculations to determine if the compensation is appropriate or if multiple disorders are present. Okay. Stop me if I'm going too fast and it seems like I'm missing or you're not catching a step on this, because this can get a little bit technical. First of all, there's no such thing as overcompensation. The body does not function that way. It only compensates to get the pH back to normal, and it doesn't go. If you're seeing something where the compensation appears to be overcompensated, there's probably a secondary disorder going on. Excuse me, a secondary primary disorder going on. Not as a compensatory mechanism, just there's something else going on with the patient. If there is no compensation or the compensation is less than expected, it could be because the compensatory organ cannot do it. So, for instance, if I have long-standing COPD and I have a diabetic crisis, the compensation would be to hyperventilate, but if I got long-standing COPD, I might not be able to functionally do that. Could be that there has been enough time, especially when we talk about renal. You're not going to see that compensation there. Or it could be that another disorder, primary disorder, is present, and it just happens to be working in the same direction. And that's kind of where we're going to look at. I blew this chart up for you in the back, I think, and you may want to pull it out to use as we're walking through these. Okay. Is it there? Oh, I know it's there someplace. Take a look at Module 1, or Module A. Is it there? Oh, it's in there? Okay. There you go. So what this is showing, this is from Dana Oakes, who you may or may not have encountered as far as the little pocket guides. He has a book on blood gas interpretation that I pilfered this from, so I owe him credit. But looking at respiratory and acidemia and alkalemia, and dividing them into an acute process versus a chronic process, and looking at how much of a change occurs and what the effect of that will be on a pH and a bicarbonate. Metabolic acidemia and metabolic alkalemia only are chronic because it takes them longer to work. It's not like the respiratory system works within a matter of minutes. So even with that, there's a small fudge factor that we have built in. Our goal is to fully explain why the values are the way they are, specifically the pH and the PCO2. We'll allow a little bit of variance in there. So this is the way he approaches it. What's the primary problem? Acidemia or alkalemia. Who's causing it? CO2 or bicarbonate. Is there compensatory response there? We come up with an initial classification. We then go ahead and evaluate that compensatory process and see if there's the presence of some other abnormality being there. For all metabolic acidemias, you will need to calculate. You will need to have electrolytes so you can calculate the anion gap. And Mary will talk next Thursday a little bit more about that. Take a look at the oxygenation. Does it correlate with the patient and the accuracy? And then finally get an interpretation. There's some factors that obviously are going to complicate the body's ability. Chronic lung disease, as I mentioned previously. Chronic renal disease. Sometimes some therapeutic interventions that we do, i.e. hyperventilation for removal of CO2. Or some of the mixed acid-base problems will come. Let's take a look at that COPD problem, first of all. Here's a blood gas. How would we classify this in our normal classification scheme? Okay, fully compensated respiratory acidosis, right? It is an acidosis. It's on the acid side of normal. The CO2 is elevated, so it's got to be a respiratory problem. The bicarbonate is out of range, but it's not the cause. It's the compensating factor. So our technical classification will be fully compensated respiratory acidosis. He goes into a functional classification. It's a chronic problem. This is somebody who has not just developed this problem. It's somebody who has long-standing respiratory failure. So using our rules that you have there, let's see if this makes sense, if I can justify this. First of all, my change in CO2 from normal is 15. My change in pH is 0.02 pH units, and my change in bicarbonate is 7. Everybody see where I got those from. Okay. Going from the midpoint of the normal range. So my CO2 change of 55, for every 10 torr change in PCO2, there's a 0.03 change in pH because it's a chronic problem, right? So that means 10 torr, 0.03. I have a 15 torr, and I want to solve for that, okay? I did it a little bit different here. I just divided that 15 by 10, which is what you're going to end up doing anyway. So 0.03 times 15 divided by 10, 0.03 times 1.5, just so you can see where I got that number from. If you were to do it the longhand, because all this is a ratio. If 10 torr is going to move that pH 0.03 units, how much will 15 move it? Good so far? Okay. Well, it's going to move at 0.0545, which means that my pH predicted would be go from 7.40 down 0.045 units to 7.36. Come on. Okay. Well, they don't match, do they? 7.36, 7.38. For every 10 torr change in PCO2, there's a 4 milliequivalent change in bicarbonate. Again, multiplying by 1.5 because for every 10 torr change, there's now a 4 unit change. Comes up to 6, so 24 plus 6 would be 30. However, there's a discrepancy between the 31 that I have and the 30 that I calculate out. So something else must be causing a little bit of an increase in bicarbonate. So I look at the other value that we have there on the bottom, and it says for every 1 milliequivalent change in bicarbonate, there's a 0.015 change in pH. So I go ahead and add that 7.3 point. It works out to a 0.15 change. So adding that to my 7.36, I come back to 7.38. Dead nuts, right on target. But it also means that it's not just solely a respiratory problem. There's some metabolic issue going on also. It's a compensated respiratory acidosis with a secondary metabolic alkalemia. It's not just solely a respiratory problem. Why? Well, maybe they're on steroids and diuretics, and that's causing a hypochloremia and a hypokalemia, which will lead to an alkalosis. That was fun. Erica says no. It's all just a matter of walking through them.
Can I walk through some more?
Sure. Let's say I got a patient who has these blood gases, but I know this is a chronic CO2 retention problem. Well, this is what you would expect to see, but if they're hyperventilating secondary to perhaps some hypoxemia, you might see the gas on the right, which if you look at the gas on the right, we would classify this as a metabolic problem, but it's not. It's just that acute respiratory alkalosis superimposed on a chronic ventilatory failure. So you need to, again, whenever I see a metabolic alkalemia, first thing I always think of is this really a respiratory acidosis? Is this really a chronic ventilatory failure that's hyperventilating? Because as you'll find, metabolic alkalemias are pretty rare. Everybody follow the train of thought there? Acute on chronic. And if I want to correct that CO2, I'm not going to correct it back to 40. I'm going to correct it back to bicarb divided by 0.6, which works out to 52. You've got to be careful of that one. What if I had COPD and I had a hypotensive episode? I know that I'm going to have some problems with oxygenation delivery, which means I'm probably going to have a problem with normal Krebs cycle activity. But this is the guy's normal blood gas on the left. These are the blood gases that I see on the right. Well, it's not that they're magically normal. That bicarbonate has dropped because of the acidosis that is present. Need to take and look at the bigger picture. It's not always as simply saying, well, that's a normal blood gas. Not for this guy, it ain't. Yes?
What if you don't have it?
You have to have it. Yeah. Then you use your other clinical assessment skills that you end up having. If I got somebody's got a barrel chest, if I have somebody who has a known smoking history, they have a little tag on their wrist that says, I have COPD. Give you an idea. Renal failure can distort the values also, because we know that that's the way that the body regulates bicarbonate and electrolytes. So we always want to go deeper with especially with a metabolic acidemia. Those therapeutic interventions I was talking about, mechanical ventilation, all kind of drugs that can alter these. So here, Dana wanted to try another one, so let's try another one. Okay. How would I classify this just the way we've always done? Not a normal blood gas. Fully compensated respiratory alkalosis. Okay. It is on the alkalotic side, but it's normal. CO2 is reduced, so that's the cause. Bicarb is out of range, so the lowered bicarb would not be causing an alkalosis. This is the compensatory mechanism. We said it's going to be fully compensated respiratory alkalosis, or more specifically a chronic respiratory alkalosis because the bicarb is fully compensated back. Okay, let's go through my process again. 18 is my PCO2. There's a 22 torr difference from a normal CO2. So for every 10 torr change in PCO2, there's a 0.03. Again, I'm using the chronic line. And that means that 22 divided by 10 is 2.2 times 0.03 again is a 0.066, which adding that to my normal pH says that my pH should be 7.47. Okay. What about the bicarb change? For every 10 torr change in CO2, there's a 5 milliequivalent on the alkalosis side. So that means that 2.2 times 5 is 11. 24 minus the 11 would be 13. The compensation says it should be 13. In reality, it's 12, though. So something else must be creating a little bit of acidosis to be able to drop that down. There must be an underlying metabolic acidemia superimposed on this respiratory alkalosis. How do I know it has to be a respiratory acidosis? How do I get from here to here? From 7.47 to 7.44. It's a drop in pH. It's got to be a metabolic acidosis that's causing that. I also know because my predicted is 13, my actual is 12. Something's dropping that bicarbonate level more. which would be a metabolic acidemia.
So there's no degree of like variation with bicarb?
No. It's all calculated. Yep. For every 1 milliequivalent change in bicarb, there's a 0.015 change in pH from your table. I go ahead and it's about 0.2, close enough. So that would bring it back to 7.45. Which is right on target. It's within the degree of variation. So I have a fully compensated respiratory alkalosis, but I also have an underlying metabolic acidosis present. The compensatory mechanism doesn't fully answer the question. Again, sometimes it's a mixed problem that is present. If two opposing problems coexist, say I got an acute renal failure causing a metabolic acidosis and pain causing a respiratory alkalosis, going in opposite directions is going to look like a normal blood gas as far as the pH is concerned. But really, there's two problems simultaneously there. Let's try another one. How would I classify it? Rick, I thought I knew how to classify this. You're playing with my with my brain. Fully compensated fully compensated metabolic acidosis. Okay, good. The acidotic side. It's not the CO2, but rather it's the bicarb. There is compensating present, so we're going to call it a fully compensated metabolic acidosis. And let's go through our process. Starting with the bicarbonate now, not the CO2. We know that for every 1 milliequivalent change in bicarbonate, there's a 0.015 change in pH. So we're trying to predict what the change in the pH will be based upon that 7 milliequivalent drop in bicarbonate. Doing so, we would find that it would go to 7.30, which doesn't match our pH. Rat bastards. So we also got to look at what change in CO2 that would have based upon that 7 milliequivalent drop in bicarbonate, and that should predict a PCO2 of 32, which doesn't match our other one. So is there something else going on from a respiratory standpoint superimposed on that metabolic acidosis? There's a 11.6 change. For every 10 torr change, there's a 0.0 change in pH. And in that case, we would end up having 1.2 times 0.08 or 0.096. Add that to my pH. I have 7.4 within the margin of error. So I have a mixed metabolic acidosis, and simultaneously I have a respiratory alkalosis, part of which is compensatory, part of which is something's going on in the respiratory centers. More than meets the eye. Can you have a triple disorder? Why not?
Yeah, throw it in there.
Yeah, you can. But for this one, we need to calculate something called the anion gap. We've talked about the anion gap before, right? Mm-hmm. And something called the bicarbonate gap, which I know we haven't. Anion gap is just basically your sodium less your chloride less your bicarbonate. Normal value, ordering donuts, 6 to 12. Above 20, we start to consider that abnormal. The concept of a bicarbonate gap is if I take that bicarbonate, add to it what my existing anion gap is, less 12, and you can say that there is 3 different possibilities that are there. The normal value here is 20 to 28, and if it's within that 20 to 28, if the bicarbonate gap is within that 20 to 28 range, then I would say I have an anion gap metabolic acidosis. When Mary talks next time, she'll talk about some metabolic acidemias are anion gap greater than 20. Some of them are normal. Less than 20 would be a mixed anion gap metabolic acidosis and a non-anion gap metabolic acidosis. And if it's greater than 28, it's an anion gap metabolic acidosis and a metabolic alkalosis. What the hell is he saying? I know you're thinking this. Let's go through it. Okay. So if the anion gap is normal, we're not going to worry about that process. Alkalemia. CO2 is reduced, which would cause the alkalemia. Bicarb is reduced, would not be the problem, so it's primarily a respiratory issue that we're dealing with some compensatory drop in bicarbonate. At least that's what we're going to start with. Tentor change, 0.038 change in pH. I know it's got to be a chronic problem because the bicarb has changed. So minus 10 tentor change. I have a tentor change, so that means that it's a 0.03 change in pH, which brings it to 7.43. Not even close to my 7.52. How about what effect does that have on the bicarb? Tentor drop in PCO2 equals a 5 milliequivalent change in bicarbonate level. So my bicarb starts at 24, goes down 5 to 19. My bicarb is 21. So there must be some other issue going on here. I look at my bicarbonate change for every 1 milliequivalent change in bicarbonate. Looking at my metabolic alkalosis on the bottom, there's a 0.015 change in pH unit, which means that should come back to 7.46. Still not there. So some additional metabolic alkalosis must be present to move me from 7.46 to 7.52. So I have a respiratory alkalosis. I have a metabolic acidosis. I must have a metabolic alkalosis there also. We look at our anion and bicarbonate gaps. Our anion gap says 23, and that must mean we have a metabolic acidosis. The cause of the metabolic acidosis is in a group that you're going to learn is called the mud pilers, because they have a high anion gap. More on that later. Looking at the bicarbonate gap, 21 is my bicarbonate. The anion gap was 23, so 23 minus 12 is 11. 21 and 11 is 32. We go back to that one. Oh, I'm going to go all the way back. Go back to that one slide, though. It says that must mean that I have not only an anion gap metabolic acidosis, but I have a metabolic alkalosis superimposed on there. Holy moly. Respiratory alkalosis and a metabolic acidosis, not as a compensatory, an actual problem, and a metabolic alkalosis. Does that sum it up? This is an example. I have a patient who has a pneumonia who's hyperventilating secondary hypoxemia, respiratory alkalosis. He also has azotemic renal failure, so that's going to cause a high anion gap metabolic acidosis, and he has hypokalemia secondary to diuretic therapy. For us, we're trying to improve that azotemia by increasing urine output. Unfortunately, we're losing potassium. So he's probably hypochloremic. Remember, the only way then that it can get rid of the acidosis is to dump bicarb, or dump potassium, excuse me. Is that a real problem that could exist? Absolutely. We would just totally miss it unless you dig a little bit deeper. And if you talk to a lot of the pulmonologists, they'll say, well, yeah, of course you got to do that. But up to this point in time, we haven't. Can you have a quadruple disorder? No. You can't have a respiratory alkalosis and a respiratory acidosis simultaneously. Whew, thank God. All right. On the next test, there is one question that deals with this. This one coming up. I will provide you this. There's only one. I will provide you with that chart. Yes. Okay. Now, in Malley, nobody pays attention to this, but in Chapter 14, which is actually a very fabulous chapter to read. Okay, I'm stretching it a little bit there, but it is interesting. He has this, what he calls an acid-base map, okay? And these are basically shaded areas where there are specific respiratory or metabolic problems. The lines that are they're called isopleths, whatever they are the bicarbonate levels. On the right side is the pH, on the bottom side is the PCO2. Why he includes the hydrogen ion concentration, I have no idea, because no one's going to ever look at that. So what you do is you take a piece of paper, and you put your piece of paper where the values you want are. So I'm going to cover up at the 7.35 point. I'm going to cover up at the 60 point, and look where it lands. Chronic respiratory acidosis with a bicarbonate level of about 32.5. This distance here, 32. It's right between the two. Got it?
Where do you see the bicarbonate?
It's right here. This is 30. This is 33.
Oh, okay, got it.
So maybe 31 and a half. So line up the pH, line up the PCO2, and that's where we fall. Not only tell us what the bicarbonate calculated would be, but it also says, hey, this is a chronic respiratory acidosis problem. I like it. Here's another one. pH is 7.6, PCO2 of 30. Line them up 7.6, line them up 30, look where it falls. Doesn't fall within one of the bands, which means it's not a primary disorder. This is one that would say, ooh, I got a little bit of a respiratory alkalosis, but I also have a little bit of a metabolic alkalosis. It's caught between the two of them. Does that make sense? 738 PCO2 is 70. Line them up. There's my bicarb around 42. And again, it's outside, so there's probably a little bit of a metabolic alkalosis and my respiratory acidosis because it's between those two bands. It's a quick and easy way to kind of get where you're at. 73530, well, that falls right in the middle of a metabolic acidosis. And it's consistent. So, take a look at, if you want, from Chapter 14 in Malley. What some students have done in past years is taken this, taken that acid-base map, laminated them together, put them on their name badge. I kind of like it. Next Tuesday, we'll begin Module K. I'm a little bit off sequence here, I understand. Mary will cover the beginning of this module next Thursday. And then on the 11th, we'll have an exam. And on Tuesday, I will also have a practice test for you. And there is a study guide out.